live on a restless, ever-changing planet. A world that supports life, yet also a place full of dangers. Hundreds of millions of people are affected by natural disasters and extreme events every year.
Why does a storm suddenly take off? That's a really big question.
Because of the size of the Japan earthquake, the axis of the Earth actually moved and it changed the length of the day.
So in the western US, this loss of fresh water supply will certainly impact our quality of life.
To help answer these questions, scientists and engineers at NASA's Jet Propulsion Laboratory are conducting research, building and testing instruments, and analyzing data. In August 2005, Hurricane Katrina strengthened quickly over the Gulf of Mexico. It left $100 billion of damage in its wake, 700,000 people homeless, and almost 2,000 people lost their lives. 5 years later, Hurricane Earl became the first major hurricane to hit the New England coast in almost 20 years. But Earl never became as intense as Katrina. Though it caused damage, it quickly lost strength over the Atlantic Ocean. The question NASA scientists are trying to answer is, why the difference in the two storms?
Sometimes hurricanes just rapidly intensify, and other times they don't. You could imagine a storm's about to make landfall, and if you think it's going to be a Category 1, you may be able to deal with the consequences. If it intensifies to a Category 4 within a matter of hours before making landfall, that could be the difference between no lives lost and lots of lives lost. NASA recently found that the intensity of storms are closely related to the amount of water vapor in the atmosphere. We can see storm activity real-time with satellite data. The way that the satellite data streams work is they're almost instantaneous. We could observe right now what's happening around the world with NASA satellites.
The AIRS instrument on NASA's Aqua satellite provided global maps of water vapor, which are used to extract data about the two hurricanes.
Hurricanes are gigantic heat engines. They basically convert energy, heat energy that was in the ocean, to winds and rainfall and movement in the atmosphere. And they do it through evaporation of water vapor from very warm ocean waters. And that's the fuel that you need to create a hurricane like a Katrina.
To get even more detail about water vapor, NASA built an instrument called HAMSR. It can fly directly over the eye of the hurricane aboard an unmanned aircraft.
HAMSR has helped us make unique observations about the temperature and the water vapor structure within hurricanes at a level of detail that we've not had before. It addresses the observing blind spot inside of hurricanes. Unmanned aircraft like the Global Hawk have been used to study storms to peer inside of them. It pulls back the cover of the top of the storm and it sort of peels it away and you can see inside of it.
No one instrument or satellite can provide the whole story. Understanding the complexity of extreme weather involves the coordinated efforts of many agencies, including NOAA, and a number of other governmental institutions, universities, and research groups.
The research that we're doing here at NASA will have either indirect or direct benefits to people living in the path of storms, where their lives are at risk and their property is at risk.
California's Central Valley is one of the world's most productive agricultural regions. It has always been rich with water. In contrast, the dense population of the Los Angeles region has become dependent on imported water. Take the water away, and instead of 16 million people, this area could sustain less than 500,000. Where does most of this water come from? Snowmelt from the Sierra Nevadas and Colorado Rockies.
The water supply that's brought in the aqueducts, about 75% of that water comes from snowmelt. So there's a natural handoff of water. When the human-made reservoirs release water, it's at about the same time that snowmelt is coming in. The mountain snowpack is melting earlier in the year for different reasons in different places. And that water that used to come in as snow, which would sit there and wait, falls as rain and runs off immediately. And that displaces water out of the reservoir, and that water eventually is lost out ultimately into the Pacific Ocean.
One of the primary sources of snowmelt runoff for the Los Angeles region is the Colorado River Basin. Since 2002, the demand for water has increasingly exceeded the river's supply. This gap is projected to continue to grow. One surprising reason: dust.
I was climbing a peak in Colorado with my father and my brother, and we dug out an area, just scraped dust off of the snow surface, and it exposed clean snow. We came back later in the day, we could see just this column of clean snow. All the dirty snow had melted down away from it, and it had melted less during that day.
It has melted less because clean white snow reflects more of the sunlight and heats up more slowly. The dirty snow absorbs more sunlight and melts faster. The grazing of cattle and sheep, and more recently, all-terrain vehicles stir up the dust. Today, vast areas of the Rockies are covered by dust.
So the dust causes the snowpack to melt faster and causes that water to get into the rivers faster and causes the rivers to rise faster. That made me realize, looking at the whole landscape, this is a huge water resource impact. The amazing thing about working at the Jet Propulsion Laboratory is that we can pick and choose technologies that have been developed for Earth missions as well as missions that are exploring the solar system. I'm the principal investigator on a new technology that we're developing here, and it's the combination of technologies on an airplane, and it's called the Airborne Snow Observatory. In the coming decade, NASA and JPL have spaceborne missions and airborne missions that will allow us to understand the global and regional water supplies.
Japan has one of the world's most elaborate networks of earthquake detectors. But these sensors would underestimate what happened on March 11, 2011. At 2:46 in the afternoon, a magnitude 9.0 earthquake struck 43 miles off Japan's Oshika Peninsula. This was the biggest earthquake ever to hit Japan, and one of the 5 largest recorded on the planet. It generated a massive tsunami that killed nearly 16,000 people and left millions without electricity and water. As the call went out for assistance, scientists from around the world volunteered to help. They began analyzing satellite data about what had happened. By the next morning, a team of scientists at JPL and researchers at Indiana University had gathered to study the data.
We were some of the first people to see these space images. When we looked closely and saw the devastation and damage to the bridges, the houses, and the nuclear power plant, we were deeply affected. One of the frightening tasks that we had was to look at the before and after images of the Fukushima nuclear reactor, which was hit by the tsunami and damaged by explosions. When we responded to the earthquake, we were given images that were collected prior to the event so that we could compare them with images that were collected after the earthquake. This helped the responders figure out what kind of damage might have occurred in the nuclear reactor area. For example, what parts might have been damaged by the explosion and what parts might have been damaged by the earthquake or tsunami. We felt that we needed to get the information about the nuclear reactor to the Japanese quickly because it was impacting so many people's lives.
Analyzing data for the Japan disaster is just one example of the ongoing research and modeling taking place at JPL.
In California, there are about 20,000 earthquakes a year that we measure, but most of those are too small for us to feel. And the earthquake's the part we can feel, but the ground keeps moving and those faults keep moving for years. That's a very interesting result we never even knew about until we had these spaceborne measurements. Using aircraft equipped with radar, we can study how the strain accumulates for earthquakes, and then we can image earthquakes after they've happened. We have an array or a network of GPS receivers scattered all over Southern California. There are hundreds of them. And from this, we can see the motion across the fault. So we can actually measure the plate tectonics in real time. And we want to know where the earthquakes are going to occur and how big they're going to be and in what sort of time frame. In the future, NASA missions will be used to study the entire globe, as well as the entire U.S., and our computer models will become more and more accurate.
Researching, modeling, forecasting, and analyzing the forces that affect hurricanes, earthquakes, and freshwater availability are just some of the ways that NASA helps us understand our ever-changing world. From the land, from the air, and from space, NASA, together with agencies and researchers around the globe, is working to make us safer on this planet we call home.